problem. Hopefully you've never seen this before. This one is about counting what's called as substrings. So here's the problem. Okay, let's start with the problem statement. Well, before I tell you what the problem is, I have to give you a definition, because otherwise this thing won't make a whole lot of sense. First of all, if you're given a string, a substring is any contiguous set of characters within the string. Okay, and we're going to call something as a good substring if it satisfies this condition, that it has at most k zeros and at most k ones. Okay. So it's not allowed to have more than k zeros or more than k ones. Fine. This is what we're going to call as a good substring. And what we want to know is, if we're given a string, we want to know, and not only are we given a string, we'll also be given an integer k, and this k can change. It's not something fixed. Okay. Is that yours?
No, it's Ricky.
It's me?
Oh, Ricky sent a message, I see. Yeah.
Oh, yeah.
So we'll be given a string, and we'll be given a number k, and we'll be given queries. We'll be told in the string, I'm asking you about just this portion of this long string, and your job is to report the number of good substrings in this part of the string. Okay, so you're allowed to do whatever is needed in order to make this happen. Is the problem clear to everyone? Yeah.
What's the minimum length of a substring?
Minimum length is that's a good question. I guess even a zero length thing is you could count this. Yeah, I should say something about that here, but that only changes your number by one, so it's okay. It's not a major deal, right? You're checking whether the audio is
Yeah.
good?
Yeah, it's good. Okay.
Yeah, okay. So given some string, we want to know for a given k how many good substrings there are. So let's do a quick example just to make sure we understand this, right? So we're given, let's say, let's say this is our string, and let's say k is equal to 2. And let's say we want the number of good substrings in this entire string. Fine? So how many are there? Looks like it could be a pretty large number, right? By the way, the same substring from a different location is considered a so what do you do if there are repeats? I didn't quite write that down here. So a 0, 1 here is a good substring, right? But the same 0, 1 is also is a good substring, and we're going to count it twice because it's in a different location. Fine? So we don't care if it's repeated somewhere, if this substring is repeated somewhere. If it's in a different location, it's a different substring. All right? So if I'm asked to do this, I could just think of all possible. I don't know. There are many different ways to solve this problem. All right. Here is one. I'm going to give you an obvious way to solve it, so that so that we can get started and we can then figure out how to do it better. So what I'm going to do is I'm going to initialize this count to 0. All right, and then I am going to set. I'm going to choose I to go from 1 to n, and j also from 1 to n, and then for each. So think of I as the start point of the substring. Think of j as the end point of the substring. And I can write a separate subroutine that checks whether this substring from I to j is a good substring, and if it is, then I will increment the count. Okay. This is sort of the naive way of doing it. There's you should be able to come up with this fairly straightforwardly because that's just the definition that's given to you. Is this much clearer? Okay. So it's a good idea often to write down at least a first version of the algorithm so that then you have a baseline and then you can try to improve this. Now, at this point, it's worthwhile to think about, do you think this algorithm is a good algorithm? Well, in order to do that, it's worthwhile to try and analyze its time complexity, and then we would have a basis to compare it with other things. Are you with me so far? So what is the time complexity of this?
N squared.
So clearly there are two nested for loops. And so therefore this if statement is going to be encountered in roughly n squared number of times. But the problem is that
What about the method? We don't know what.
well, we don't know what this cost is, but good substring is easy to verify according to our definition. We just go from I to j, count the number of zeros, count the number of ones. If either of them goes over k, we throw it out. Right? But how long does that take us? Well, so here I'm just going to say this is actually, I've written down as n cubed, but it's actually n squared times k. Really the time complexity is something like n squared times k, because any string that's more than 2k, you can already throw it out. Because either the number of zeros will be too much, or the number of ones will be too much. Is that clear? So if you have any sequence of length 2k plus 1, we know that more than half of them is going to be, well, whichever is higher, zeros or ones, will be more than k. So therefore, it won't be a good string. So that means we don't really have to worry about very long strings. We can improve on some of the time complexities here. But anyways, if I do it in this naive fashion, it's something like n squared times k. Is that clear? All right, so now we'd like to improve on this. And there are many ways to improve this, but before I tell you any answers, let me listen to your suggestions for this. What are obvious improvements that you can make? Yeah.
If we track like how many ones or zeros are in a row, if we go over k ones or over k zeros, then we know that substring can't.
But that comes in the checking for good substring, right? So really, much of your time complexity comes from here, which is n squared, right? And then this one here, we already know that it's not really n cubed, it's n squared times k. We'll assume that k is smaller than n because n is the big string and k is some smaller number that you're given, right? By the way, if k is larger than n, then what? Then if k is too large, then what happens? What's the answer? Every substring is a good substring, and so all you have to do is to report the number of substrings, which is a slightly different problem, and maybe there are other ways to do this. right? So really the interesting case is when k is much smaller than n, and if k is much smaller than n, then really the time complexity here is n squared times k. Is that clear? All right. So, any thoughts on how I would improve this?
I'm just thinking, I don't know if it's correct or not. So we could have, like, in addition to the array, we could have another pair.
Okay.
The pair's first element will count the 0.
Yeah.
Pair's second element will count the 1.
Yeah.
And whenever we get a query of L and I, we will just subtract the pair count.
Well, so for now, this L and I actually is just confusing things. So let's just assume that we want to find this in the whole string.
Oh, okay. So the thing is, like, the only thing is it will improve the good substring part, but I think it will still be having the n square into the good substring part will be like reduced by the subtraction of it, I think.
Okay.
I don't know.
All right. So let me come back
I
to
have a
you.
part, so for the j value,
Uh-huh.
do we have to start with 1 to n?
Right,
Or
so-
can we say,
So clearly, it doesn't make sense to have j to be smaller than I. So we could start from I plus 1,
Yeah.
for instance, right?
no, I was thinking, because you said 2j plus 1 is if you have a string length of 2j plus 1.
2k plus 1.
2k plus 1, you know that that's not a good substring.
Right.
So what if I use that for the j condition?
So what are you going to change here?
So there, I don't need to do 1 comma 1 comma 2, because you know that there's going to be no, right?
But you have to tell me how the code changes so that then I can do time complexity.
So it should be,
Hold on just a second. Yeah.
So instead of j from 1 to n, it goes j from I to I plus 2k.
That's roughly right.
I plus
So
1 to
so j, first of all, it's never going to be smaller than I. So you can replace this 1 by I, and you can replace this n by I plus 2k, because the moment it goes to 2k plus 1, it's not going to work out for you. Or is it 2k minus 1? It may be 2k minus 1. Doesn't really matter, but essentially this for loop will only go 2k times, right? So then your time complexity has now become,
2 and
they go of n times k squared. Why? Because the first for loop goes n times, the second for loop goes only 2k times, and the good substring you're spending order k time to figure out whether it's good or not, right? Okay, that's good. What else? So we'd like to figure out improvements by basically doing some observations, some useful observations. And the first thing you guys did was j, well, we said the obvious thing, we said that j needs to be, actually it's greater than or equal to I, it's not just strictly greater than that, j needs to be at least I. So that's one improvement. What's the other improvement? We said that the substring should not be of length, every substring of length at most k. Yeah, this actually you haven't quite talked about it, so let me hold that back. You said that every substring of length more than 2k is bad, so we use that information. Anything else?
So if a substring is length k, then the most zeros it has is k, or the most ones it has is k, so it has to be good.
That's right. So if it is k or less, it can't have more than k zeros or more than k ones, and so automatically it becomes good. So if it is too small, it's always good. If it is too large, it's always bad. So somewhere in between, we have to do some work. Okay. So that's what this says. Every substring of length at most k is good, and the answer, the reason is just what he said. I should have added another one that says every substring of length more than 2k plus 1, more than 2k is bad, and that also is easy to see. So therefore, this J only needs to go somewhere in between, right? Roughly speaking. So therefore, this code now can be modified in this fashion. I initialize a count. I goes from 1 to n. And then I'm going to simply count how many short substrings there are, right? Because I don't have to go and individually count them. I know exactly how many there are going to be. So I might as well stick them in there and then only deal with the slightly longer strings. And here I can go from I plus k up to I plus 2k. I don't have to go all the way up to n. So that's going to be another improvement here, right? And I only have to worry about those strings. Is this clear? So I saved some amount of work because for the short strings, I can compute how many substrings of length at most k are present in them, right? It'll become more clear as we do an example, but for now I'm trying to see if you have better ideas on how to improve this.
I have one idea. So let's say we fix like the left, then at some point it's gonna become bad, right? So I can maybe do some binary search on this.
Binary search. Okay.
If I keep some prefix sum of the zeros and ones,
Yeah.
I can sort of binary search this value.
Okay, so he thinks that, so Ricky's suggesting that, long strings are bad, but maybe even a little bit earlier things will go bad because maybe there are too many zeros or too many ones. And perhaps we could do a binary search on where that thing will happen. Does that make any sense to you guys? So his suggestion is to do binary search for the place where things start to go bad. I see some blank faces.
I
so
don't understand how.
you don't
No.
understand.
Yeah, I don't know what the.
Okay. Maybe I explain it more thoroughly.
Hold
okay.
on. Let me. So okay. Well, we'll come back to binary search. Why don't you think of other ideas? It turns out you can do even better than that. So let's think about other ideas for how we go about counting number of good strings. Remember, in the end, we want just a count that says how many good strings there are, right? And our approach so far has been, let's go find each one of these suckers and then count them. And somehow that seems like too much work.
I think.
And
like
then
this-
after you look at each substring, we have to go and verify that it is a good substring, and that seems like a lot of work. Especially think of n to be 1,000,000. So let's say we have a 1,000,000 length string, and think of k to be, I don't know, 100 or something that's fairly large, 100 or 1,000. And so you're going to get a lot of different substrings, right? And if it is by the way, if n is 1,000,000, and if k is, let's say, 1,000, n cubed is already out of reach for us because that's 10 to the 18, right? Or n squared k is unreachable. N times k squared is 1,000,000 times 1,000 squared, and that's a billion. That's already a lot. You'll be spending a lot of time looking for these things and checking whether they're good or not. So we would like to do something a lot better with these long strings. Yeah? Yeah?
So instead of, or like one thing we could do is we could add variables to track the current number of ones and the current number of zeros.
Okay, from where? Because your substring could start anywhere. Okay, but let's say we have some reference point, and we're counting zeros and ones, and then what?
And then if the number of zeros and the number of ones goes over k, then we know it's a bad substring.
Okay.
So we can just move our starting point forward by one.
All right, so you are suggesting to count the number of good substrings starting from every possible point. Is that what your approach is?
No, like, instead of using for loops, you would use pointers, and then your point, your first.
Right, but
yeah.
at least the way I understood your suggestion was we'll take every possible start point for this substring, then we'll find
Oh, wait.
we'll find longer and longer ones, and then the number of good substrings starting from this point is what we will add up, and then we'll go to the next point and start all over again. Is that correct? Okay. So so the suggestion here is to try every possible start point. So think of this as your I, and then look for good substrings starting from here, and then report them. And we know that we don't have to go past 2k, right? And so we could count those, and then keep doing this.
I have an idea, like, let's start from the end.
Uh-huh.
Let's say 2 is the k,
Yeah.
and the string is 0, 1, 0.
Yeah.
Like when it's 0,
Yeah.
its count is increased. When it's 1, count is increased. When it's 0, the count is increased.
Yeah.
Once you encounter 0, you are exceeding the count.
Exceeding the
Count.
it becomes
So
a bad
you're
string.
checking the first letter.
Mhm.
It is 0. So you increment the I. You come to 1, and
Okay.
you are incrementing the count again.
All right.
Okay. And since
So essentially, you're trying to figure out what makes it bad, and then you're trying to see if you could eliminate it from the left
Yeah,
end.
from the left end.
But then, are you sure you're not missing anything?
oh, I am.
Then it's a
I am.
problem.
Yeah. Sorry.
So you have to make sure you don't miss anything in your counting, right? That's important. Yeah.
Like, if we have a good substring and it's long, then we already know that every smaller substring of that is also good.
Ah,
So we don't
very
have
good.
to start
Okay.
at every possible starting point. Once we
Excellent.
get to the end of the
Excellent.
long substring, we can move forward
Yeah.
past it.
So what you're saying is the following. That's not what you're saying. Sorry. You're saying if a string is good, then every substring of it is also good. Right? So over here, for instance, if this is a good substring, so every substring of this is also a good substring. You don't have to worry about it, because if that substring didn't violate the number of zeros or ones, even any part of it is not going to violate it either, right?
Is that true though? Because if I have 0, 1, 1, 0, 1, 0 as my substring,
0 what?
0, 1, 1, 0, 1, 0.
Yeah.
So this
Well,
is
if k
valid.
is 2, if k is, remember,
is 2.
if k is 2, then
If I
your,
chop off,
this is a valid substring.
right?
Sorry, it's a good substring. So is this, so is this, and so is this. Then there are many more actually.
The 0, 1, 1 would be a valid substring, but it's not good because it
Why not?
has, oh, less than, or it's not exactly k or less.
You can't allow more than 2 zeros or more than 2 ones. Right? That's what you're told.
Well, I guess it would also hold the other way around as
Ah,
well.
what is that?
Well, if a substring of size j is bad, then any substring of size more than j is also bad.
Any superstring of that thing is also bad. So these are two basic principles that will help you. One is that if a string is good, then any substring of it is also good. If any string is bad, any superstring of that is also bad. Because if you've already exceeded it, if you increase, if you widen it, it's only going to get worse. Is that clear? Is that clear? I'm not receiving feedback from you. Is it yes?
Yeah.
Okay. So I need to. I'm trying to see if I can find good strings and bad strings, because that will help me eliminate a lot more, right? So how do we utilize this? So let's start with one of them. In this case, it says if a string is bad, so is every superstring of this. What this means is, if I have, here's a bad substring. This has 3 zeros and only 3 zeros and 1 1. So it's already exceeded the number of zeros. So this is a bad one, right? Now if I extend it any more in either direction, it's only going to get worse. There's no point in doing that. So therefore, superstrings of bad strings are bad. Now, we can use that in a nice way by doing the following. What we can do is the following. We set I to any variable between 1 and n, so meaning we try every possible left endpoint of the substring. We know that if they are short, then we know exactly how many possible substrings there are. Actually, that is incorrect. It should just be k, not k times k plus 1. Sorry. What we're going to do is we are going to count the number of good substrings from every possible start point and do this over the entire string. Fine? So if we start here, then the short ones are easy, because anything that's of length at most k, if this length is less than or equal to k, we know that it's never going to violate the rule that we have of too many zeros or too many ones. And how many substrings can you have that start here? It's just going to be 0, 1, 2, 3, 4, 5, all the way up to k, right? So we get to add k over here. I think we also have to make it k plus 1. I need to change this again, sorry. So we can count the first k plus 1, we don't even have to look at them. But then after that, we have to go from I plus k, but we can stop at 2k. But here we can exploit the fact that the first time we find a bad substring, we can stop this for loop and jump out of it. So if it is a good substring, we count it. Otherwise, we fall out of this for loop, because there's no point in counting anymore for things that start with the same start point, right? We're proceeding along this. The first time we find a bad substring starting from I, we can stop these because anything beyond this is already going to be bad, right? So it helps to stop the for loop a little bit slightly earlier than is needed. Is that clear? So now that means this is, well, it's still standing at n times k squared. So we need one more good idea, and this one is the other one that you pointed out, namely if a string is good, so is every substring of it. How are we going to use this? So the way we're going to use this is, instead of, we'll just find the longest, starting from I, we'll just find the longest substring that is good, and then simply count all the substrings that lie within it. So we don't have to do all that work of checking each one whether it's good or not. All we need is the last one that works. And there you had suggested binary search, but actually there are other ways to do it as well. And we'll see what that is. I think I still have one more mistake here. I should fix that as well. So here, what we're doing is, we're just simply counting the first k plus 1, because until we reach k, nothing happens, nothing bad will happen, right? And then we go from k to 2k, and for each one, at least for now, we're just doing the number of good substrings of things that are between I and j. And so we're going to see how to do this differently, and that's what the next slide is about. So more good observations here. So far we know that if we have a good substring, then every substring of that substring is also good. We know that for every we know that if a string is bad, then every superstring of that is also bad. And we know that if a string of length p is good, we can figure out how many good substrings it has. Okay, because that's easy to count. You don't need to know what those strings are, and you can directly count it. And here I made a mistake here, but we'll see that very soon. All we need to do is to count this, and if for every pair, if A to B, what am I saying? It's a substring, we just count them not very clean here. I want to say something different here. This is what we're, so let me step back from this, and the slides are actually quite confusing. Let me try and explain to you directly here. What we're doing is the following. We're given a long string, okay? And we're asked to count how many good substrings there are. We're going to, for every possible start point, we'll count all the good substrings that start from here. Okay? And then we'll move on to the next place and do the same thing over again. So for any given start point, how do I figure out the number of good substrings? For this, what I'm going to do is, I am going to start from here and keep looking at each character. Keep track of the zeros and ones, and until it crosses your limit of k, we know that everything that you see is a good substring. So to contribute 1 towards your answer, right? So somewhere it'll stop and it'll say oh yeah, the next substring that starts here, that goes from here to here, is not a good substring. The moment you hit a bad substring, you know that anything after that is not worth looking at, because all those are superstrings of the start one, and so therefore we don't need to count, right? Now here is something else that happens. If I'm starting over, if I look at the next start point, let me use a different color. If I move to the next start point, now, if I look at all these substrings, what can we say about them? Because these are substrings of what you already know is good, they're also good. And so I just need to know how many there are. I don't need to go and look at them and verify this again. So a lot of the work can be avoided, and you can start at the next next place where you had a bad substring for I. So for I, if J is the last place where you had a good substring, then for I plus 1, you only have to start from J plus 1. You don't have to look at anything before that, because all of those are going to be good. Is that clear? And so that avoids a lot of counting for you, because you never have to go back and look at things just because you move the left end point. And so we'll just keep accumulating our counts and continue to move forward. And so what we'll do is we'll have a left end point, and we'll have a moving point for the first place where there's a transition from good substring to a bad substring, and then we'll just keep going with that. So let me show that with an example, and hopefully it will start to become clear. Okay, so let's say we're trying k equals 2. All right. So if k equals 2, that means we won't allow 3 zeros or 3 ones, right? So if I'm going to start at this location, I'll have the empty string, I'll have a 0, I'll have 0, 1, I'll have 0, 1, 0, and that will be the end of it, right? If I try to add one more 0, it will fail, and so therefore I get 4 substrings for this location that are good substrings. Okay. Now what happens with the next possible location? Let me use a different color. So starting from position 1, I can see that. Oh, this won't work. So for starting from the start here, we know that there are 4 substrings. Actually, let's not include the empty substring. So let's just say 3 here. So for anything that starts at position 0, we know that there are 3 substrings that are going to be good. Okay. Next, I'm going to move our start point to this place here and begin the counts again. The only thing is that I don't have to count till here, because all of this is going to be a good substring, right? Because that's only a substring of something that you already decided was good. And so therefore, it's just going to be 3 minus 1 that I will count from here, and then start to look beyond this. And now I will get one more, which is going to be fine because I have 2 zeros, and I'll get one more, that's going to be 2 ones. And that's where it will stop. So you will get 4 for the second location. Is that clear? Then I'll go back to moving the left hand point to the next guy here, and again I will avoid counting these three because I know they're going to be good. And again, you can go one more and stop, and so you'll get 4 for this location. All right. I'll go back to moving this left endpoint, and now I'll be able to go one more before it becomes bad. Actually, did I get that right? Yeah. Okay. So again, I will have 4 from here, and then I will move it again to this guy here, and again I will only get 4. Then I have I'll start from here, and this time it will be able to go one more, but it won't go any more than that because it'll end up over here. So from here it'll only give me a 3, and so on and so forth. Is this becoming clear? Is this making sense? So what I'm doing is I have 2 pointers, one that's keeping track of the left end of the substrings I'm counting, okay? And the other that is keeping track of the first place where I get a bad substring on the other side. And both of them never go back, they all keep going forward. All right, so that's really the idea behind this algorithm. The real question is, yeah, go ahead.
Can we also, so we mentioned 2 ways, one was every superstring of a bad substring is also
Those were
bad.
2 main observations.
And then
Correct.
the other was, yeah. And so here we're using
We're using both in this approach.
Mhm.
Why? Because when I move the left end,
Right.
I don't count for anything up to from here to here because they were substrings of good strings. And also, when I found the first bad string with starting from this left end point, I didn't go beyond this because I know they're all going to be bad. So I used both
Right.
key observations.
Instead of finding the first bad, can we start from the last and find the first, the last good?
It's the same thing, they're going to
Yeah.
be next to each other.
Yeah, yeah.
The last good is going to be just before the first bad.
Right.
So,
Um,
how does it change anything?
Yeah, nothing, I was just wondering if potentially we can start from the very last and then.
You can't start from the very last. That's not very smart because then you will be looking at those over and over and over
No,
again.
the last of the 2K interval, not the last of the whole.
Still too bad.
Oh, okay.
Because if K can be 1,000.
Right.
So what are you going to do? You're going to keep running from the other end as much as it takes to find the first guy. Here, I never look at the same thing twice again. That's critical. Without understanding that, you're not going to see that this is a good algorithm, right? Neither of these pointers ever look at the same character twice. I keeps moving forward because in each iteration I'm just moving right. J keeps track of the first place where this guy, or the last place where this guy encountered a good string, and then for I+1 I start from there and keep going. I don't go back and look at things that I've already looked at. So my right endpoint always moves right. So therefore, it is bound to have some good properties. If you go back and look at things and count them again and again, then you're going to get things like this. So the key question now is, what is the time complexity of this range algorithm?
All
Yeah.
of them.
O of n. Why is that?
Because we're only iterating all the way through from the beginning to the end.
Yeah.
Technically twice, which is O of 2n, but we remove constants. And the only other calculation we're doing is just counting the number substrings within a bigger good substring, and that's just like a constant calculation. Okay.
You don't believe that? Anyone agree with this statement
Yeah.
or disagree? Anyone disagree?
I,
Do you want-
I don't know,
You're
but
not quite-
I feel it's not OFN, but I don't know why. I'm like, I don't know.
You want to try that again?
What she said, I understood, but like you eventually iterate it 2 times. Right?
Yeah, so it's
Two
only
times
two times as
is
opposed to-
not the problem. You're missing the key point there. Two is still a constant. What do you mean 2 times?
No, 2 times means you iterate over the array 2 times.
Which iterates over the array 2 times?
Like if we say I and j, for example.
Okay.
I will go.
I iterates and j iterates, yeah. But there are only 2 variables and they're allowed to iterate over. You're allowed to go and look at the array twice. It's still going to be O of n.
Like for example, let's say the array length is 100, for example,
Yeah,
and your good string is length of 99.
yeah.
So let's say you start I with 0, your j will go till 99, right?
So let's say n is a million.
Okay.
Or yeah, let's go even higher. Let's say n is a billion.
Okay.
Okay, and let's say k is 1,000. All right. So now what is going to happen for the first point? I have to go and find the first place where what? There's a violation of this good property, right? So you're going to look at all of this. So I will stay here,
Yeah,
and J will move until it finds that point where the definition breaks.
Yeah.
Then what happens? Next, I will move to the second place,
You will go-
and then what?
you will start from j.
Start from where?
J plus 1.
Start from j plus 1. I'm not looking at this again. Okay? So j is just progressing to the right, I is only progressing to the right. That's the key point. And you're going to compare, you're going to do some comparisons or counts or do some work.
Yeah.
But you never go back, so you're not doing 2 nested for loops. Because there you're doing for I equals 1 to n, for j equals something to something, so that's a nested for loop. Here you're not going to get a nested for loop.
So basically n plus n, so we go.
Well, you will have a nested for loop, but it won't go back and look at old things again. Is that clear? So how do we write this pseudocode? These are all the observations that we made. I'm not going to repeat all that. So the basic idea was we count the number of good substrings that start at any given position, and then we make sure that for the next position we know that the first position where things are going to break are going to be further than where we were before. These are all things that we know based on the observations.
Can I just have a small question?
Yeah.
So let's say after my 10 I iterations,
Yeah.
I reached end with j,
Yeah.
then I stop. Do I stop there?
Remember, j is always going to be ahead of I.
Yeah, that's what I'm asking. Like, if, let's say after 10 or 20 I's iteration, I reach end of the array with j. Do I stop there or still I will continue with I?
End of what?
Like 10 to the power 9, for example.
You mean j hits
J
the end?
hits the end, yeah.
J hits the end.
Yeah.
When j hits the end, I is not that far behind.
Like, I'm just
Okay.
asking.
Yeah, I'm trying to tell you, just hold on.
Mhm.
So let's say that somewhere you reached I here and j has reached this end.
Okay.
Now, I still have to count this guy, I still have to count all those positions, right? How much work do I have to do for each one of them?
I think it's constant.
Constant.
Why is it constant?
Sum of
Because
factors.
I'm not going to look at them, I'm simply going to increment my count appropriately. So therefore, J will just stay there and I will come and finish up. Is this clear? So, can you help me with the pseudocode? This is roughly the, let me not show you those things. How do I work out the pseudocode? What are the things that I have to keep track of? So I'm giving you a clue here. I'm saying I'm going to keep track of something called rightmost. The rightmost of L is the first place, or sorry, it's the last place where the string from L to rightmost of L is a good substring. The moment you go beyond that, it's bad. Is that clear? So for every L, for every position, I have something called the rightmost of that position. If I go beyond that point, I'll only have bad substrings that start from I. Okay? So is that something, what do we know from these examples that we looked at? What do we know about the rightmost L as L increases?
It could just be a variable outside the loop.
That is fine, but you're not understanding my question. I'm saying what is the behavior of rightmost of L as L progresses?
It's always greater than L, and it will always keep progressing to this right.
Right. So as L progresses, rightmost of L also progresses, only to the right. Does that make sense? Which is sort of what we said earlier, but because we are using this concept, it needs to be clarified. Okay? Now, so really we have to keep track of this rightmost of L because the first time around, I can find the rightmost of 1. It's a bit of work. But then, what about for 2?
Like it can stay there. When
For 2, it could stay there or it could go further. Right? It could stay there if all you're removing on this end is something that was already less than K. Right? In that case, you won't be able to go further, but that's okay. At least you know that it's never coming back, it's only staying there. But rightmost of L essentially only progresses that way, L only progresses this way. And we just have to keep track of how things are going. Now, so what we're going to do is for every position in the string, we're going to keep track of the rightmost value, which tells us what is the last place where good substrings end for that start point. And so that's what we're going to call as the rightmost array. Now, if I had the rightmost array, then it's easy to count the number of substrings that are good starting from L. Why is that? Here is my string, here is my position L, here is my position rightmost of L. How many good substrings do I have that start at L?
it's let's say n is equal to that difference in length, and
It's
it's
basically this difference,
sum of
right?
the number.
Yeah. We don't even need the sum
But-
because we just need the number,
Mhm.
right? It's just this difference. And really that's all you need to know. So if I can keep track of L and rightmost L, if I can figure out all the values, then all I have to do is to subtract rightmost L minus L and add them up. Fine? And so that means when I go from L to L plus 1, if I can figure out what rightmost of L plus 1 is going to be, then I'd be in pretty good shape. Right? And we know that rightmost of L plus 1 can never be to the left of rightmost of of L. You only have to go this way, although it could stay at the same place. And this pretty much gives us the source code, the code for this, or the algorithm, pseudocode for this algorithm. And I'm going to show you what I have here. Right. So here's what it does. For every possible value of L, we're going to keep track of the rightmost L, which you understand, right? That's the first place where things start to go back. You'll also keep track of the number of zeros and the number of ones up to wherever it is you've scanned it. And count of L is simply the number of substrings that start at L, or the left endpoint is L, and the contribution that it gives to the overall count. So now, let's assume that we've computed all of these for one position L. We want to know how to go and figure this out for L plus 1. Okay. So, for this L, for any general L, I have figured out the rightmost of L. I've also figured out the number of zeros here and the number of ones here. And I've also figured out the count, but the count is easy because it's just this minus this. Right? So if I've kept track of the number of zeros and ones here, how do I figure out the same values for L plus 1? That's what we are left with deciding.
So that would just be if L was a 1, you would subtract 1. If L was a 0, you would subtract 1.
So you'll have two different cases. One is when this character is a 0, and one is where this character is a 1. And each one will have a slightly different behavior, but pretty easy to figure out. Okay, so that pretty much gives us the pseudocode. What do I have here? Yeah. So if that character that you're looking at in the ith position is a 0, then, well, first of all, you have to initialize the number of zeros for L plus 1, number of ones for L plus 1. The rightmost of L plus 1, you'll just initialize it to what it was before, right? Except that if it were a 0, the number of zeros will become less because you've gone one place beyond. All the other numbers, we know what the values are, for now at least. And then we're going to scan from position rightmost of L until we find the first place where the definition breaks down. Right? And for that, we'll just, every time we hit a 0, we'll increment the count of either zeros or ones, and whichever becomes too large, that's where we will go and that's when we'll know we've hit rightmost of L plus 1. And of course, here it's if S sub I is equal to 0, so the ith character is 0. If it's 1, it's going to be the exact opposite, where you'll start with decrementing the value of the number of ones, and then find the rightmost. So really, you're all done here. Once you figured out count of L for each position, you just have to add them. That's just a linear time addition of counts. So the great thing, of course, is that well, let's figure out what the time complexity is. What is the time complexity of figuring out count of 1? What I've told you here is that this could take a while. Actually, it's not order n, it's going to be order k. It's not quite. I wasn't precise in writing these. This should be order of k. But then, once you've computed the value of count of 1, how much time do you need for figuring out count of 2. That's the big question. Do you have an answer for this? If for each one you end up spending order k time, then you'll be in trouble, then you'll get n times k. If you spend only a constant amount of time, you'll get big O of n. But really, once you hit once you figured out rightmost of L, how much time does it take to figure out rightmost of L plus 1? Is it really a constant?
If both are same, something with same and difference only, but I don't know. I can't.
What if they, well, let's say that you've encountered all zeros, okay? So if you hit all k zeros, you know you're going to hit rightmost L already. Then, after that, if you have a string of ones, what happens?
You'll keep adding.
Sorry, so let's say k is equal to 2. So let's say I start with 3 zeros. And then 3 ones, and 3 zeros, 3 ones. Let's say I have something like this. How much work is it to find the next rightmost value? That's the question, right? So over here, I would have to look at all 3 of these in order to figure out that the rightmost is 2, right? Then when I move this over, I have to go quite a bit further before I figure out that the rightmost is hit, right? Which means that it's not a constant anymore. So what do I do? How do I now, because you guys said it was linear time. And if I go with that, it might appear that I spend only constant amount of time every time, but that's not true.
Okay, like let's say 2k is equal to 2, and when you it's 0, you found the right.
Well, try k equals 1000, then what?
K is equal to 1000. Let's say there are 1000 zeros.
First time, forget it. Yeah.
Okay.
Let's say the first time, we can spend a lot of work and figure it out.
Yeah.
But what happens after
Let's
that?
say 1001 is also 0.
Mhm.
If both are 0 and we find the I is also equal,
Right.
then we can just increment I and progressing with j.
Fine.
If it is different, right? Let's
You're telling me what the code looks like, and you're
Uh-huh.
absolutely right. But I want to know how many times that loop goes through. Because if it's a
Okay.
constant, then I can simply say constant times n, right? If it's not, then I can't quite say constant times n. Right? So as we go down the string, if for each one, if I'm spending only constant amount of time to update the value of rightmost, then I'm in great shape. Because then I know how to count it and add them up. Yeah?
So I think it's to find count L plus 1, the maximum time it would take would be k.
Fine. But if you say it's k, then really your time complexity becomes k times n. Because in the worst case, this could happen a lot. So is it k times n, or is it just n? Order n?
I mean, I think it's still order n, and it was previously said
Yeah.
that these pointers never decrease, they're
Yeah,
always
right.
increasing. So
That's
we may
right.
do a lot of work in one single count,
Right.
but over the long term, over all iterations,
Correct.
it doesn't pass n.
So this uses something called the concept of amortized analysis, where you're saying, all right, sometime I may move a lot, but then overall, when I add it up over all the movements, it's going to be only big O of n, because it can't move beyond that.
So-
And we're never going back.
If for, let's say at position L, I do K amount of board.
Yeah.
For position L
For
plus
one
one.
position, yeah.
I would only do one step further, right?
No, so there are examples like this one, where the rightmost for 0 was, sorry, I need to provide position numbers properly here. Let's call these positions as 1, 2, 5. Let's say we have something like this, right? So the rightmost of 1 is 2, because anything beyond that, I'll have a third 0, and that won't be acceptable. The rightmost of 2 would be also 3. Well, actually, no, sorry, because I can now go all the way up to there, right? The rightmost of 3 will stay there. Rightmost of 4 will also stay there. Rightmost of 5 will go beyond, will go all the way to here, right? So what you will see is that sometimes you may not move at all, sometimes you may move a little bit, but sometimes you may move all the way k steps. But if you add these over all the movements, then it can only move for a total of n, because of what we said earlier, namely it only moves to the right.
But that didn't, at least I didn't understand how what you just explained disproved what I said.
It disproved what I said. How did I say you were wrong? All I said was questioning you to answer my question,
Oh, okay.
and I didn't quite see an answer, that's all.
Okay.
I didn't say you were wrong.
Okay.
I was asking you to think more about how to prove categorically that it is big O of n. And what I just said essentially proves it categorically, because I and J only move to the right. We will have something like a while loop, where either I will be incremented or J will be incremented, but not both. Okay? And for each one, you'll do a count. By J, I mean this is actually rightmost of I. This algorithm is simple enough that you can write it easily, but it's complicated enough that it's worthwhile for you to write it formally, because it's very easy to make mistakes here. That's one of the reasons why I'm putting it down. So by the way, to give this time analysis a little more formal footing, I'm saying if I'm given count of L, and then I need to figure out count of L plus 1. In order to do that, I have to first figure out what rightmost of L plus 1 is. But the amount of time it takes me is actually proportional to rightmost of L plus 1 minus rightmost of L. It's saying beyond rightmost of L, how much further do I have to go? If I go whatever number of steps, that's the cost that I incur with computing count of L plus 1. Now, if you take these values, if you add them over all the iterations, then it cannot be more than n. And that's why you get big O of n. When you add all these times, what you get is now instead of rightmost, I'm just calling it R. R of 1 plus R of 2 minus R of 1 plus R of 3 minus R of 2, and so on and so forth, because you're looking at how much you're going beyond. And when you add these up, what happens? Things start to cancel out. So your R2 and minus R2 will cancel out, R1 and minus R1 will cancel out. What's left at the end? It's just rightmost of n, which you know is exactly n. Okay, so that's the correct time complexity analysis. By the way, in each iteration, you're doing some constant amount of work, and that's fine. That only adds to the big O of n notation. Pseudocode, in case you really want to see this. Oh, sorry. So you need to initialize rightmost of one. Well, you initialize all those values to 0 for position 1, okay? And then you compute all those values by going down the string. So for the first one, you're going to spend a lot of work, but it's fine, because in the end, it will all pay off. Then, when you're done with this, you initialize your total count to just count of 1, which is the count you have so far. And by the way, count of 1 is simply rightmost of 1 minus 1. And then you're going to go from L equals 2 to N. Here, so you're going to compute all these values, rightmost of L, number of zeros of L, number of ones of L, and count of L, using the previous values and updating them. And in the end, once that loop is finished, you're going to accumulate the total count to be count of L plus 1 plus whatever you've done so far. And to figure these out, remember you're moving your left hand by 1, so either your number of zeros or your number of ones will first be decreased, and then you'll start to increase the other things as you see new characters. And so all of those will get contributed to the appropriate arrays, and in the end, all you do is report the count.
One thing in the initial problem is
Yeah.
that we had this added thing of queries. So if we have to do this many times
So if we
over.
have to do these queries, so that's a good question. Before I go there, are there any questions about this? Is this pretty clear? Yeah? No problem? Yeah.
So all the variables in like the first line are all arrays.
Yeah, they're all arrays. Yeah, all 4 of those, you can think of those as arrays. Well, actually, you can think of them as just a variable, because you're never going to you're never going to need old things, so you don't need a full array. All you need is a single variable. Okay, so Ricky's question: what if I gave you an arbitrary start point and an arbitrary end point, and I asked you, sure, thanks. Again, just based on what we know, it's enough. It's okay to spend the time that's proportional to the length of that string, which is what we would do here, right? Because we have this arbitrary starting point, we'll just start from there. If we pre-computed these values, we can, then there are different ways to deal with this. In fact, you can solve it in constant time.
In constant time?
Yeah.
Because the right endpoint is also given.
Yeah.
I had some sort of thinking, it's like, so we know that the rightmost endpoint is always increasing, right?
Yeah.
So if we're given, let's say, a query from L to R,
Yeah.
at some, let's say the first query doesn't exceed the right given value. We want to find the very first L that exceeds this R.
Right.
And
so towards the end, you have to do you have to take care of the things that go beyond it, and not count them. Count the substrings that go beyond it.
When we find this first L that goes all the way to the right, we know we can basically chop off all those right endpoints, and we have all the good substrings of this L and R.
Right.
Plus a
So
summation.
finding that location will take you log n.
Log n.
Can we avoid this? Well, for those of you who kind of missed out on why this might even be thought of as a constant, let me explain how constant comes in, and then you can think of this added new complexity here. So here's the deal. this array called count. So I have count of 1, count of 2, all the way up to count of n. Right? Once I finish with the code that I showed you, I would have all these values. Now what is count of I? Count of I is the number of good substrings that whose left endpoints are in position I, right? So it's all the things that start here and end somewhere. So we've got those counts. Now I need to find. Let's say I ask you to find the sum of values between positions I and j. How would you do this? And let's say I ask you queries. Different times I'll ask you different start points and different end points, I or j, and your job is to give me the sum of values between positions I and j. All right, it's the same array at all times. The array hasn't changed because it all came from the original string. And all I'm asking is, just give me the sum of the counts between I and j. How does one do this? Well, there's a simple way to do it. You go to position I, start from there to j, and add them. How much time will that take you? It depends on the length of, or the difference between I and j. Can you do it any faster?
Is it 0, 1?
No, it's not 0, 1. It's integers.
So
Yeah.
we still have access to like the other arrays?
Sorry?
We still have access to the other?
If you want, but in fact you don't need it.
Oh, okay.
It is 0, 1.
So they're numbers. In fact, they could even be real numbers for all I care. If they're integers, that's fine too.
Prefix sums?
You make something called prefix sums. So what I do is I'll say count. Let's call this count sum. What is count sum? It's in position I. It's going to be not just the count value of I. It's going to be the sum of the first I values that I'm going to store here. Is that clear? So count sum of I is count of 1 plus count of 2 all the way up to count of I. Fine? So let's say and by the way, how do I figure this out? Count sum of 1 is simply count of 1, right? Count sum of 2 is count of 1 plus count of 2. So all I have to do is take the value here and add count of 2 to it. So count sum of I is simply count of I. Sorry, count of I plus
Count of I minus 1.
Count sum.
count sum of I minus 1. Yes. Right? So I can now figure out additional values in constant time, and I can fill this up. So I can quickly fill up this array. If I have this array filled up, what good is it for me? How does it help me?
Well, but, okay, if you have.
Answer the question. Don't ask me another question yet.
Okay.
Because I want others to think about this.
Well,
J minus.
yeah, exactly, j
Sorry?
minus.
Whole sum of j minus.
Correct. So the sum of the values from I to j is simply count sum of j minus count sum of I, because it's the count of all of this minus the count of all of this. Is that clear? So you can do this in constant time once you've figured this out. Sorry?
To fill that, we still need that.
But I do that only once. The queries may be asked many times.
In that case.
So that's what I mean when I say query. It means queries will be asked many times, and I will do this computation only once. Okay? Now, can I use this idea for arbitrary start points and arbitrary end points for good substrings? That's the question. And here it turns out that there are some wrinkles. things don't quite work out. So let's say I figured out all the counts, and also I've done count sums. If I tell you that I want all the good substrings that lie between this and this position, what can you do? Remember, I can count count of I plus 1 and so on and so forth, but I'm only allowed to count substrings that don't go beyond here, right? And that's where the problem is. So I'm only going to count those for which the what did I call it? Rightmost is less than j. For those guys, I can count them fully. For the others, I have to put in more work. But I could still perhaps get around it. Because I still have to only do rightmost minus, I'm not sure.
You have to take maybe a minimum, like if we know the right.
Yeah, you have to do a minimum for each of those pairs.
And doing that, it's a little annoying. So that's why I'm saying like this binary search.
It's not clear. Yeah, at this point, it's not clear if we can do this in constant time, but
Yeah.
definitely we can do this in log n time, because we can. Well, even log n is not trivial.
Yeah.
Perhaps you guys should go and try and figure this out. I know I'm way past time, so let me stop here. But this is a good question to think about. How to deal with arbitrary start functions, arbitrary answers. Okay? Thank you.
Thank you, Professor.
Thank you.